Thank you very much. I would like to say a very warm welcome and a big thanks to all the local heroes and champions and to everyone who has traveled across the world to get here and contribute to this workshop. Did I say who I am? He said who I am. Yes, good. That's a good point. I don't need to. Sir Guy, I would just like to point out that I think I was promoted since you did that talk, because I'm a full professor now. You can note that down. So the three key points I would like to get across is that the Southern Ocean is globally important and it's changing. And that understanding these changes and their impacts is critically limited by lack of data. And that we can, must, and will do better. And this requires strategic planning, coordination, and prioritization of the observations. This is a point one. This is a sketch of the Southern Ocean. It's characterized by the Antarctic circumpolar current, which is moving around the continent. In addition to that big, strong current, there is some overturning going on, water moving in, getting in contact through eddy exchanges and through upwelling, bringing water towards the coast. This water comes in contact with the surface, so you have surface fluxes and stuff going on. You have sea ice freezing and melting, dense water creation, carbon dioxide being removed from the atmosphere together with other gases. And the sea ice impact the physics. The presence of sea ice makes the carbon exchange different. And the physics also dictates how the life is faring. It provides a habitat and it provides a changing environment for the biology. There's also a lot of ice tied on the Antarctic continent, and this ice is affected by the ocean. So the ice-ocean interaction affects sea ice, sea level rise globally. And this overturning in the Southern Ocean and sinking of dense water masses affects climate globally. The Southern Ocean is also a connector. It connects all the major oceans on Earth. And changes taking place in the Southern Ocean is transmitted to every major ocean basin. And we have observed some changes. Some things are changing dramatically. There are big warming signals and freshening signals. This study was published several years ago, but it caught everyone by surprise how strong these signals are. It's 0.2 degrees warmer, 0.1 PSU fresher. Other changes were not as obvious. This is a time series, on the right, there is a time series of the Antarctic circumpolar current transport. It's 20 years of data of the Antarctic circumpolar current and eddy kinetic energy. And here you can't see such a clear change, but it's a change taking place on smaller timescales, almost cyclic on these 20 years. And it could also be a change that we can't observe the change, but it could well be that it's more longer time scale. There is also changes taking place in the glaciers. They are melting. They have been melting for the last 10,000 years, but since we started to observe them with satellites, the melting seems to accelerate. And there is it's well motivated to study this problem. There's so much ice tied up in the Antarctic continent. Much of that ice is below sea level. So it's a big global challenge, actually, to understand and be able maybe to predict how sea level rise will be in the future. We have many coastal, heavily populated areas on Earth, both in the western, eastern, and northern and southern worlds. Some are more prepared for sea level rise, and some are not well prepared for it. There is changes also on larger scales. There is observed decline in krill and increase in salps. There is trends in sea ice with large regional variations that you can see here. It's in this case, it's almost a symmetrical pattern around the continent. This graph shows how Gen2 penguins increase, Adelie penguins decrease. The second point is that these changes that we have observed, or think we have observed, are only the tip of the iceberg. The reason for that is that the Southern Ocean has been and continues to be one of the world's largest data deserts. Every one of the changes outlined has been identified using data from a very small number of sources. Ship-based measurements, and there are very few ships in the Southern Ocean, especially in winter, or shore-based measurements, and Antarctica is the least inhabited of all the continents, especially in winter. Instruments deployed from ships, such as floats, moorings, etc., which are invaluable, but they are sparse and they are easily lost in these hostile conditions. And from satellites, which are also invaluable, but they only measure the very surface layer, and they need ground truthing. The existing observing system elements are the GO ship, where you have regular ship transects. They were started by WOS. They measure tracers, carbon, ocean physics. It's an international agreement. But they are rarely, with some exceptions, they are occupied about once per decade. And also they don't extend onto the shelf areas. There is a SOOP, there is the continuous plankton recorders, there are some moorings, there are the Argo and AUVs. Red means very few data points. Instrumented seals, satellites, etc., etc. Yeah. So the problem here is that it's as you approach the Antarctic continent, all these measurements get more and more sparse. For example, the coverage of profiling floats drops off dramatically when the sea ice zone is reached. The sustained moorings coverage is very poor, except for the Weddell Sea, and the WOS lines are very sparse. So a sobering example is the BAM's paper coming out, which now includes a Southern Ocean section for the first time. And what we could assess for 2014 was surface temperature, circulation from sea surface height, sea ice, etc., all this from satellites. They don't work in ice-covered regions, so there we couldn't get. Upper ocean heat content, mixed layer depth, some water mass changes from Argo, small bits about the shelf regions, but very regionally dependent, small bits about carbon from underway sampling primarily. And what could not be assessed? Deep ocean water masses, besides small bits of repeat hydrography, biogeochemistry across very large scales, nothing under the sea ice, besides from the small bits in the Weddell Sea, nothing under the ice shelves, no biological variables, aside from some very specific sites, etc. So overall, if you look at the Southern Ocean in domains, you can divide it into 5 domains. We have the shallow water in the deep sea region, the deep water in the deep sea region, the shelf region, under the region under the ice shelves. So the part of the shallow water outside sea ice is partly covered. As soon as you come under the sea ice, we have problem. We have problems in the deep ocean where you need to go with a ship in order to measure. On the shelf, we have problems due to the fact that we need heavy icebreakers to get there. Under the ice shelves, it's very, very hard to get, very resource heavy, demanding very expensive resources. So in fact, if you look at all these boxes, it's only about half of the first box that we are anywhere near to measure anywhere close to with the frequency that we would like. So this is a bottom-up initiative, sort of. It has been recognized by researchers worldwide that this need, these gaps exist. So we work together to develop SOOS, Southern Ocean Observing System. Our goal is to facilitate internationally, or the mission statement, facilitate internationally the collection and delivery of essential observations on variability and change of Southern Ocean systems to all stakeholders, researchers, government, and industries, through design, advocacy, and implementation of cost-effective observing and data delivery systems. How am I doing with time? A little bit. 4 minutes. Thanks. And that is important for a number of reasons. So these are the science goals. Again, we would like to understand these science questions. And this is the vision. If we look 20 years into the future, there will be a number of platforms measuring all the things we need. They should measure at a sufficient rate. These platforms will be integrated components with a cyber infrastructure that will bring all those observational platforms together to form an observing system. The first question to ask is, what is absolutely essential to measure? How often do we need samples, and where should the focus be? How should we measure? So we work together with all the international efforts to define what, when, and for how long a quantity should be measured. And it's called EOV, Essential Ocean Variables. And this definition is sort of the core of the real design in this system. This is where the design takes place. The first big challenge. For physical oceanography and sea ice, it wasn't so hard to see this. It's generally accepted by the community. For example, temperature, salinity, ice thickness, and so on. The biogeochemical variables are being defined globally and will be tailored to Southern Ocean specific requirements. For example, iron needs to be included, which is not globally. And the biological EOVs, that is a key milestone for SOOS, that there has been a community-agreed process for identifying what a biological EOV is, and a list of candidates. Biology is so much harder than physics because there are so many variables to choose from, and so many groups of variables. So it's they're sort of behind physics, I suppose you could say. So SOOS is working with the community to compile all international standards and methodologies, and is advocating for their use by all nations. So one of the big challenges is that we have a limited number of heavy icebreakers, not likely to increase in the future. On the contrary, they might decrease. We need to stop being depending on these heavy icebreakers if we want to make the measurements at the rate we want. We need to move towards greater automation. A positive thing is that stuff like this, this is a glider, they are increasing rapidly and they are likely set to continue. I think that's a good place to stop. Thank you.